now, in Osaka, a student named Sora is about to tell her brother in London that she was accepted into a deep-sea research expedition. She presses send on a live video call. That single connection relies on a highly sensitive digital stream of multimedia. Her camera and microphone are simultaneously capturing video frames and audio frequencies, stitching them together with text and interface graphics into one continuous flow of data. To cross the planet, her voice and image are broken apart and converted into light. This glowing green pulse is one of those packets, racing through a glass core thinner than a human hair. The success of Sora's conversation relies entirely on this solitary pulse surviving the 9,000-mile journey across a globally shared network. But her packet is not traveling alone. Millions of other packets, carrying web searches, file downloads, and software updates, are pouring into the exact same cables at the exact same time. By default, networks process this traffic using a rule called best effort delivery. It is a strict first-come, first-served system. The router treats an urgent syllable of a live conversation exactly the same as a fragment of an invisible background update. This diagram shows a physical pipe, representing what network engineers call bandwidth. Bandwidth is a strict physical limit, the maximum data carrying capacity of a network link within a given time period. Once a cable is laid, you cannot expand the capacity of the pipe to accommodate a surge in traffic on demand. Looking at this same diagram, you can see what happens when friction is introduced. The actual rate of successfully delivered data is called throughput. Throughput is almost always lower than bandwidth because data ends up slowing down and backing up as it moves through crowded junctions. Physical issues deplete throughput even further. Electromagnetic interference along copper cables frequently corrupts the ones and zeros inside a packet. When a router detects a high error rate, it forces the sender to retransmit the damaged data, wasting capacity. This is why best effort delivery fails for live video. When a fixed bandwidth connection fills up with random data, the network has no default mechanism to protect the throughput of a real-time call. Beyond the volume of the data, the success of the call depends on the timing of the journey. Latency is the total travel time required to move a single packet from its source to its destination. That total delay is built from 4 compounding delays. Propagation delay is the physical travel time of light through glass. Processing delay is the time a router takes to read a destination address. Serialization delay is the time required to push the bits onto the wire. And queuing delay is the time a packet spends sitting in line inside a router. This animated timeline shows a problem called jitter. Packets enter the network at perfectly regular intervals, but because of those compounding delays, they end up arriving chaotically. Some packets take 50 milliseconds to cross the ocean, the next might take 150. To correct this, devices use the holding zone you see here, called a jitter buffer. The receiving computer intentionally delays playback slightly. It catches the irregular packets, lines them up, and releases them outward in perfect equidistant intervals to keep the audio smooth. Buffers can smooth out minor variations, but if the queuing delay inside a router grows too large, the buffer empties before the next packet arrives. The live conversation breaks apart. The ultimate threat to a packet happens deep inside the hardware. When millions of signals converge on a single routing junction, they are forced into temporary memory queues.
If that queue fills to its physical memory limit, the router executes a tail drop. A packet arrives, finds no space, and is instantly discarded. Sora's green packet is next in line. It is traveling straight toward a completely full queue, facing unpreventable destruction. If a web page drops packet, it silently requests it again. If a live video feed drops a packet, that split second of audio is gone permanently. Without an intervention system, the network destroys the connection it is meant to facilitate. Milliseconds before the drop, an active defense system intervenes. This is quality of service, or QoS. QoS relies on packet marking. As seen here, the green packet emits a specific digital tag, commonly a DSCP marker. This vibrant indicator immediately tells the surrounding hardware that this packet contains highly sensitive voice and video data. This diagram demonstrates virtual queues. Devices read priority tags and split the dense stream of mixed traffic into separate parallel queue lanes. Once separated, handling allocation algorithms take over, automatically pulling Sora's marked packet into a faster, guaranteed bandwidth lane, bypassing standard traffic entirely. To prevent any single type of traffic from monopolizing the entire router, engineers apply shaping and policing tools, dropping excess packets to maintain balance. QoS does not create more bandwidth. It acts as a ruthless triage system, actively degrading background traffic to guarantee survival for the most sensitive data. A single router prioritizing traffic is helpful, but Sora's call passes through dozens of nodes between Japan and the United Kingdom. Engineers have two macro architectures to coordinate this triage across the planet. This is Integrated Services, or InServ, a stateful system that guarantees resources per flow. The RSVP protocol moves along the path, using T-spec and R-spec requirements to trigger physical reserves of hardware memory at every router before the transmission even begins, creating an exclusive tunnel. The alternative model is Differentiated Services, or DiffServ. Instead of mapping out individual tunnels, DiffServ broadly groups traffic into classes. Routers don't memorize individual calls. They simply check the priority tag and process based on class behavior. InServ provides flawless control, but the global internet cannot handle the memory overhead required to track billions of individual tunnels. Because DiffServ is stateless and scalable, it is the standard mechanism operating across the backbone of the internet. Bringing these standards online requires a heavily structured deployment. Network engineering teams execute a phased process: planning, design, testing, deployment, and constant monitoring. If an engineer applies an aggressive QoS policy without validating hardware limits, a router's processor will overload, bringing down the entire segment. A step-by-step rollout ensures the algorithms align with the physical reality of the servers. Protected by this careful implementation, Sora's packet completes its journey. Unharmed by jitter or tail drops, the green pulse safely exits the fiber optic cable and emerges into an external port in London. Engineers evaluate the success of this delivery using the Mean Opinion Score, or MOS. It is an empirical 1-to-5 scale used to grade the subjective clarity of voice and video after it has been reassembled. Marcus receives the call. The video is sharp, and Sora's voice is perfectly synchronized with her expression. This moment of human connection feels effortless, but it is an engineered illusion maintained millisecond by millisecond by invisible QoS traffic controllers.